In this lecture, we are going to learn about what we call the integrating factor method. So the method applies to the first order linear differential equations. So what we're trying to do is we're going to solve first order linear differential equations. So the method we are going to learn today is what we call the integrating factor method. Integrating factor method. So this is a method we use to solve first order linear differential equations. We can talk about those words later. Before we do that, let's look at the secret behind this technique. So let's look at the motivation part. So what's going on here? So the motivation. So let's look at this problem. Okay, let's look at this problem. So the problem is so consider the differential equation. Consider the differential equation. This one, let's say x² dy over dx plus 2xy equal, let's say something, cosine x plus 1. I just pick that function for the moment. So this can be any function on the function on the right side, can be any function of the independent variable. We also notice a few things here. You can see that this is simply the derivative of that. Okay, so you can see that 2x is the derivative of x². So that is a must for these kind of problems. Okay, so sometimes it is given like that, sometimes it is not the case. Now this is what we can notice. So we notice that from the product rule, so let's say recalling the product rule, so we have, if you write the product of the two functions x² and y, so what are you going to get? You're going to get, so let's say the product, what's the product rule? So you know that the uv product derivative is uv prime vu prime, right? uv prime vu prime. So if you use that result here, what's going to happen? x², that's u, v prime means dy by dx, plus v, that means y, u prime means 2x, I'm going to write it 2xy. Okay, so that is the vu prime. You can see that that is exactly what you see on the left side of the equation. Okay, so if I call this equation a star, so you can see that this is exactly what is on the left side. So that means you can replace the left side. So we can say thus, we can rewrite star as the left side is simply the derivative, so we can replace that side by this. So this is like a reverse argument, we're going to go backward. Okay, so that is simply x² y, d over dx x² y, that's exact, and then our right side is the same. So what we did is we rewrite the equation star in this form. We can see that the left side is simply the product of the derivative of the product of x² y. So now what we can do, so here we have taken the derivative. So now what we can do is we can take the inverse process, that means we can take the integral. So if you integrate this one with respect to x, so the derivative is going to go away. Okay, so we can do that. So if you integrate So we can integrate with respect to x. Integrate with respect to x. If you integrate with respect to x, you're gonna get x² y on this side, because derivative gonna cancel out now because you take the integral, and then the other side is integral of cosine x plus 1 dx. This is a very easy integral, so you're gonna end up getting sine x. So integral of cosine is sine, so so sine x plus x, and we add a constant here, c. Okay, now what we can do, we can solve for y. So what do? We can divide both sides by x². So dividing by x², dividing by x², we're gonna get y equal sine x plus x plus c over x². So we assume that x not equal to 0, and you can see that that's a solution. So you get y equal sine x plus c over x². So you can see that, so it's like a really nice argument. So we can go back and see what we did. So we start with this differential equation. We notice that the left side is the derivative of a product. Okay, so that's the major observation. So we notice that the left side is the derivative of the product. What product? x² y. So if you take the derivative of x² y, and you can see that you get exactly the left side of the equation star. So that means you can replace the left side of the equation by the derivative of x² y. And then what you can do is, since it's a derivative, we're gonna to cancel out the derivative. What we do, we're gonna integrate. Once you integrate, the derivative gonna cancel out. You're gonna get x² y on this side, and you have to take the integral of the other side. So once you take the integral of the other side, you're gonna get that. That's an easy integral. And then we divide by x², and we get the solution. So you can see that this really works. So that means the magic part behind is, you want to write the left side. You want to write the left side of the equation as the derivative of a product. Okay, if you can write the left side of the equation as the derivative of a product, then you can always do it. And that is the method what we call the integrating factor method. So we're gonna find a magic function such that this side becomes the derivative of a product. Okay, that magic function is what we call the integrating factor. So you're gonna multiply by a special function, and you're gonna make it so that it's we're gonna pick the function xi. We're gonna pick the function, the special function, so that the left side is a derivative. So let's look at the theory part, how it gonna work. Okay, so you can see that's a very nice simple argument. So let's continue. So we can start with some definitions. So the definition, a differential equation of the form ax dy over dx plus bx y equals cx is called a first order linear differential equation. First order linear differential equation. And you know why? Okay, because the derivative appear is the first derivative, and you can see that there are no product of y or its derivative, and then the coefficient function can be a function of the independent variable. So this is a first order linear differential equation. But what we normally do is, we are not going to work with this one because this is little difficult to work with. So what we do, we can transform this into what we call the standard form. So let's transform this into standard form. So standard form. So what's the standard form? If you see a coefficient function like that, what we can do, we can divide by that function. That's what we do. That's the only thing we have to do. We can divide by that. Once you divide by that, you're going to get what we call the standard form. So we're going to say dividing by ax. Okay, so whatever the coefficient in front of the derivative, we can write this one as dy over dx plus bx over ax, y equal, here we have cx over ax. Now what we can do, we can rewrite this function, this differential equation in this form. So we can rewrite this one as dy over dx plus, I'm going to call this function, this bx over ax function, I'm going to call it px. So I'm going to call that function px. Okay, px, and then we have y equal, and again the function, this function, I'm going to call it qx. Okay, so this is, I'm going to call px, and I'm going to call this function qx. Okay. So let's call that function qx. So this is what we call the standard form. Okay, so this is what we call the standard form. So in the standard form, there's a special format. It is is dy over dx plus px. The px is the function of the independent variable, and y alone, and times y equal qx. So that's it. So this is what we call the standard form. Okay, so this is called the standard form. So this is called the standard form. Okay, so we're gonna work with the standard form the rest of the lecture. So that means if the differential equation not of this form, so what we're gonna do, we're gonna divide by the coefficient of the derivative, coefficient function of the derivative ax, and then we can write this in the standard form like that. So in the standard form, it is dy by dx plus px y equal qx. It has to be like that, and this form is what we call the standard form. Now let's discuss how to solve a differential equation which is in the standard form. So every time you have to bring it to the standard form. Okay, so now goal is to how to solve such an equation. Okay, so let's talk about the theory behind. So the question is how to solve it. How to solve it. So the method is what we call the integrating factor method. Okay, integrating factor method. So consider dy over dx plus pxy equal qx. I will call this is equation 1. Okay, because we can use this a lot. So this equation 1. Okay, when you say equation 1, that's the one. Now what we can do, we're going to multiply, because you can see that we don't know. So it's very clear that the left side is not the product, the derivative of a product. It's not. So what we can do, we're going to multiply by a special function so that it's going to make it like that. Okay, so so what we're going to multiply by an unknown function, function ix. So we call ix integrating factor. It's integrating, so ix called the integrating factor. Okay, integrative factor. So I'm going to multiply by the special function. So once you multiply, what do you get? You're going to get ix dy over dx plus I'm going to write this one as px ix y, and then this here is ix qx. Okay, so that's what we have. So what we do, we're gonna simply multiply by a function ix function. Now what we're gonna do, we're gonna make assumption, big assumption, because we know that we need to make the left side the derivative of a product. So according to the product rule, so what's the product rule? uv prime plus vu prime. Okay, so that means what we can do, we're gonna make assumption that, because we already know that we have y see, we already know that we have y here and the derivative. So what we need it, we want to make sure that this is the derivative of the I function. So we're gonna set that this is exactly equal to the derivative of that. So then this is automatically become a product rule according to this side simply become the derivative of the product according to the product rule. Okay, because you have u v prime, v u prime. We have all four terms. So let's do it like that. So that's the big assumption we can do. Okay, so we can assume that. Okay, now assume that. Okay, now assume that the derivative of the unknown function is exactly equals to the px ix. So that's a big assumption. Okay, that's a big assumption. So we're going to work with that assumption. So we're going to come back to this assumption later. Okay, so that's the assumption we're going to make. Now if we assume that assumption, now what we can do? Okay, so I'm going to call this equation is double star, then I can refer to that. So you can say then the equation double star becomes ix dy over dx plus this is simply di over dx because we assume that that's the case, and then y equal ix qx. Now according to the product rule, we know that what we have on this side is simply the derivative of the product. What product? ix function and the y function. Okay, so on this side is ix qx. Now what we can do? We can take the integral. Once you take the integral, the derivative then disappear. Okay, so we can integrate. So integrating. Okay, integrating. We have I y because the derivative cancel out. You get the integral of the other side. Ix qx dx. Okay, and we know that the this integral contains the constant, but we're gonna explicitly put it there because just to avoid because if we forget that it can create a problem. Now what we can do? We're gonna solve for I. How to solve for? We're gonna solve for y. To solve for y by dividing okay, by dividing we can have y equal, so if you divide you're going to get 1 over I, the integral of I just write ix is the same thing, and then qx dx plus c. So we're gonna make sure that we put a parenthesis around because there's a c there. So that's it. Okay, so we get the solution, but the only thing that we need to know is we need to find the I. Okay, once you know I, we have the solution there. So we already have the solution, but we don't know what is I. So let's try to find it. Okay, so only thing that we need to do is now is find I. Okay, so we need to find ix. Okay, so we need to find ix. So let's do that. So how to find ix? So let's go back to our assumption. So what was our assumption? Our assumption was di over dx was we set this equal to pxi. I just call I here. Okay, and then you see that this is a separable equation, so that means you can separate them. So this is di over I divide both sides by I, and then px I multiply by dx. Now what we can do, we can integrate the two sides because this is a separable equation. Okay, so this is a separable equation. Separable equation. So this is easy. Once you integrate, you can get ln I. I don't write the absolute sign here because we need only one solution. Since we need only one solution, you can just say I. Otherwise, you have to put the absolute something, but we don't, okay, intentionally we don't do that. And then here we don't know, so we leave it like that, px dx. Now what we can do, we can rewrite this in the exponential format. So that means your ix function becomes the exponential of px dx, and you can see that this is going to give you the unknown function I. This is going to give you the unknown function I, because since we know px, what we can do, we can just integrate and put it to the e, and that's you're gonna get that. Okay. Some note. So one thing is so I'm gonna say not. You can see that we do not add AC. So that's because we are looking for only one solution. Since we are looking for one solution, we are not looking for the general solution. Since we are looking for one solution, we do not add a C in this special case. Okay, we do not add a C there. And then so now, and this is what we call the integrating factor. Okay, because that's the factor you multiply, and so we call this the integrating factor. Integrating factor. Okay? Integrating factor. So let's finish the problem now. So what we need to do is, now we're going to plug in that to the equation. Okay, so we're going to plug in that to the triple star, and then you're going to get the solution now. Okay, so let's plug in that. So we can see then we have, but don't remember this as a formula. We normally solve every time just using the definition. Okay, so y equal, we know that it is 1 over I, bracket integral of ix qx dx plus c, and if you plug in it there, so what you're gonna get is, this is I, so but it's 1 over, that means you're gonna go to the top, so that means it's gonna be e to the negative px dx, and then we have inside the bracket the integral e to the px dx, and then here we have qx dx plus c. See, there are 2 dx here. Okay, 1 dx for the top, 1 dx for the bottom, and so that's what you get. Okay, but I mean, if you want, you can write this, use this as a formula, but it will be better to integrate just using the steps. Okay, so and this is the general solution. This is the solution to equation number 1. So the question is, how do you know that you get the solution here? Okay, but there are some theories behind, so I'm going to write like a small note for that. Okay, so let's actually recall the steps first, and then I'm going to write a note. Okay, so the steps. So what are the steps we did here? So the steps are, so what's the first step? First step is write the equation in standard form. Okay, write the equation in standard form. Write the equation in standard form and identify px. That's the first step. We need to figure out what is the px. Px is the everything. It's going to count with the signs and everything. Okay, because whatever you have in front of y is the px. Number 2. So number 2, find the integrating factor. Find the integrating factor. Find the integrating factor. Find the integrating factor ix, which is e to the integral of px dx. Okay, so we're going to find that. Third step, we're going to multiply by ix. Multiply by ix, is a factor, you multiply by it, and rewrite the equation in the form, rewrite the equation as the derivative of the product ix times y is always the case, because that's how we said it, okay, always, and the other side is always ix qx. Okay, you can plug in whatever ix you get. Number 4. So this is always the case. Okay, this is always the case because that's how we pick that special I. After that, what we're going to integrate? Yeah, integrate. Once you integrate, what's going to happen? You're going to get ix y equal the integral of ix qx dx. Here, don't forget to add the c. Okay, so it's very important. It's very important. I'm going to write that here. It's okay. So we're going to add the c here. Okay, because once you integrate, you're going to get the c there. Because we need that. Okay. So I'm going to say add the c, because you're gonna like integrate, so it's a indefinite integral, so I mean you have a c in there. And then after we do that, the last step is solve for. So there are 5 steps. Solve for y. Okay, how we do that? After we do the integral, we can divide by ix. Okay, solve for y by dividing by ix. Okay, good. So those are the 5 steps that you need to do a problem in integrating factor method. So what are the steps again? So we write the problem in the standard form, and then identify what is the px. And after we identify what is the px, what we're gonna do is so we're gonna identify the px, and then what we do is we're gonna find the what we call the integrating factor. Okay, we're gonna find the integrating factor. So okay, we're gonna find the integrating factor. After you find the integrating factor, what we do, we're gonna multiply the whole equation by ix. Okay, we're gonna multiply by ix, and then what we do is we're gonna write the left hand side of the differential equation in this form. Is always the case. You can see that is always the case. It's always gonna be ix times y derivative, this side, and the other side is simply ix times qx. Okay, ix times qx. And then after you do that, then you're going to integrate both sides. Once you integrate both sides, the derivative is going to cancel out, and you're going to get ixy the other side. And then what you do after that, you can divide by ix so that you're going to solve for y. And then if you have initial conditions, you can use the initial conditions now. Okay, so so I'm going to write as a 6th step, and then to find c, use initial conditions. Okay, so we can use the initial conditions to find the c. Perfect. Okay, so let's do a couple of examples. We can do about 5-6 examples because I want to make sure that you understand this completely. So let's do examples. So example number 1. Solve dy over dx plus 3y equals 6. So the answer, and you can see that this is in standard form. So this is in standard form. Where px equal how much? Px equal, so whatever in front of y, so it is 3 plus 3 actually, so it is 3. Okay. Now what we can do, so the integrating factor, integrating factor ix equals to e to the px dx. It's always a good idea to write the formula. And then what we're going to px is 3, so 3 dx. That means e 3x, and I told you we do not add the c in this case. Okay, we don't, the special case, because we are looking for only one solution. We don't need the general solution. Since we don't need the general solution, we are not adding c. Okay, we only need just one solution. Okay, so no c. Why? Need only one solution. Okay, so that's the reason, that's why we do not add a plus c here. Okay, so let's continue. So we find the integrating factor now. Now what we can do, we're going to multiply the whole equation by that. Okay, so multiplying, okay, multiplying by e to the 3x, both sides of the equation. Okay, we can have e to the 3x dy over dx plus 3 times e to the 3x y equal 6 times e to the 3x. Okay, so now you can see that it's very clear that in this case, what is this? You can see that this is simply the derivative of, this is simply the derivative of e to the 3x. So see, you can see that from the chain rule, that's exactly the derivative. Okay, so that's exactly what we want. We need that to be the derivative. Perfect. Good. So because of that, this side is simply becomes the, so I'm going to erase that part. So because of that, this side is simply becomes the derivative of the product. Okay, so derivative of the product y times e to the 3x, just by the product rule. Okay, so this equals to 6 e to the 3x. Okay, because that's the derivative. So because of that, this simply becomes the derivative of the product. What product? Is always y times the integrating factor. Now what we can do, we can integrate both sides. Okay, we can integrate. So integrating, okay, integrating, we have y e to the 3x equal the integral of 6e 3x dx. This is a very easy integral. So this is simply 6 e to the 3x divided by 3 plus c. So I'm going to recall one of the formula that we use here. Remember in calc 2 and calc 1, or if you look at the 4 formulas, you can find this result. So we have a result says that e to the kx dx is simply 1 over k e to the kx plus c. So we can use that result here. Okay, so here k equal to k is equals to 3. Okay, k is equal to 3. So because of that, we're gonna get 2e3x plus c, 2e3x plus c. Now we can divide the whole equation by e to the 3x. Okay, so we can divide by that both sides. We can divide by that both sides, then you're gonna get y. So let's do that. So dividing, okay, dividing by e to the 3x, we have y equal 2e3x plus c divided by e to the 3x, and sometimes you can simplify. You can see we can simplify this one. So if you divide by e to the 3x, the two terms, you can get 2 plus c e negative 3x, where c is a constant. So that's the solution. Okay, so you can see that it's not that that bad. So let's go back and see the steps again. So this is equation is in the standard form. So we notice that this is in the standard form, and then so we know that the px is 3. So we're gonna plug in here and solve for the integrating factor. So it is e to the px dx. So you get 3x, e to the 3x, and then we multiply the whole equation by that. Once you multiply the whole equation by this side, is automatically the derivative term is the derivative of the product y e to the 3x always, and then equals 6 e to the 3x. Now what we do, we can integrate both sides. Once you integrate both sides, derivative going to cancel out, and you're going to get the integral. This is a very easy integral, so you end up getting 2e3x plus c. And after we do that, we divide both sides by e to the 3x, and you get the solution. Good. Okay, so I'm going to give you an exercise for you to try. So this is the exercise that you can try, and the 4 solutions of these going to be in the description. Okay, so exercise 1, solve dy over dx minus 2y equal 12. Okay, so you can see that in that case px is a negative 2, not the 2 but negative 2. Okay, so I'm going to give you that. So the px in this case simply becomes negative 2. Okay, just do the same thing and you can see the solution in the description. So let's go to the next example. So example number 2, solve dy over dx minus xy equal e to the x plus x squared over 2 along with y0 equal 1. Okay, let's put a initial condition as well. Okay, so let's see this differently. It looks like scary, is that right? E to the x plus x squared over 2, but let's see what's going to happen. You're going to see something interesting here. So the answer here, you can see that this is in standard form also. Here px is what? Here px is negative x. Okay, because everything in front of y is the px, so it is negative x in this case. So then we can find the ix. So ix is simply becomes e to the integral of px dx. So this is e to the negative x dx, and if you integrate negative x, you're going to get e to the negative x squared over 2. We do not add a c. Now that's the integrating factor, so this part is done. Now what we can do, we're going to multiply the whole equation by that. Multiplying, so we're going to get e to the negative x squared over 2 dy over dx minus x e to the negative x squared over 2 y equal e to the x plus x squared over 2 times e to the negative x squared over 2. So what's going to happen? So this, you're going to multiply two terms with the same base. So you can see that this term and that term get cancels out. So they cancel out. So you simply end up getting e to the x. Okay? So you just get e to the x. That's it. So now this side is simply the derivative of y times e to the negative x squared over 2 equal e to the x. Now what we're going to do is we're going to integrate both sides. We can integrate both sides. So after integrate, so integrating, you have y e to the negative x squared over 2 equal the integral of ex dx, which is ex plus c. Now we can divide by e to the x squared. That means you multiply by the opposite sign. So it is y equal e to the x squared over 2. Dividing by that is multiplying by the opposite sign. Okay, that's why it's a negative become positive, and then ex plus c, and you can distribute this, so you're going to get e x plus x squared over 2 plus c e x squared over 2. Okay, now only thing that you need to do is find the c, so we can do that using the initial condition. So that's the general solution. Okay, so this is the general solution. Now what we can do using the initial condition y0 equal 1, we have 1 equal y0. That means just plug in 0 where you see x, so it is e to the 0 plus c e to the 0, which so this says that 1 plus c, this says that c equals 0. Okay, so c equals 0, so that means your solution y equal e x plus x squared over 2. Okay, so this is the solution to the initial value problem. It is y equal e x plus x squared over 2. So this is the solution to the initial value problem. Okay, okay, this is the initial value problem. Good. So let's I'm going to give you again some exercise problems. So the exercise number 2, I'm going to give you 2. The first one, let's do dy by dx plus y equal x with y0 equal 4. Okay, this is x. B, how about this one? Dy over dx plus 2xy to xy equal e to the negative x squared sine x. Okay, so try them, and the solution to those problems will be in the description of the video. Okay, so let's go to another problem. Example number 3. Solve t dy over dt plus 5y equal cosine t over t to the 4th. We assume that t greater than 0, along with y pi over 2 equals 0. That's just a condition. Okay, so this is a differential equation. T dy over dt plus 5y equal cosine t over t to the 4th power. And you can see that, so the answer, you can see that this is not in the standard form. Okay, so this is not in standard form. So if this is not in standard form, what we do? If it is not in standard form, we can divide by t. So what we do? So dividing by dividing by t, we have dy over dt plus 5 over ty equal cosine t over t to the 5. So that's what happened after you divide. So now what happens? So here pt equals 5 over t. So the integrating factor it equal e to the integral of pt dt. So let's plug in there. So it's in e to the integral of 5 over t dt. This is e. If you take 5 out, it is 1 over t dt. So if you have 1 over t, that means natural log. So we just write natural log t because we are looking for only one solution. And then what we can do some algebra here. So you can bring 5 inside as a power. So if you do that, it's e to the ln t to the 5. And after we do that, we're going to use one of the college algebra result, which says that this can cancel out. So you end up getting t to the 5. So this is a algebra result of logarithmic functions. So if you have e to the ln x, which is equals to x, okay, e to the ln x equal x. So that's the result we use here. So I'm going to write it here. So there's a result. If you have e to the ln x, this is equal to x if x is positive. So we assume that x is positive. Good. And what's the other result? There's another result. It says that ln ex equal x, but this is for any x. This is for any x. But the other one is x has to be positive. So this is the result that we use here. Perfect. So that means the integrating factor simplifies all the way to the t to the 5. Okay, all the way to the t to the 5. So the t to the 5 is the integrating factor. Okay, that's interesting. Now what we do, multiplying by t to the 5th power, we're going to get t to the 5 dy over dt, plus if you multiply by t to the 5, you're going to get 5 t to the 4th power y equal cosine t over t to the 5 times t to the 5. That's very interesting. You're going to cancel out and you're only getting cosine t. So you can see what's going on there. These two terms are the same, so they cancel out each other and get cosine t. Very interesting. Now the left side is simply the derivative of y t to the 5th power. Here we have cosine t. We can integrate both sides. Okay, so we simply can integrate and you're gonna get the answer very quickly. So let's do that. So integrating, integrating, we have y t to the 5th power, the integral of cosine t dt, which is equals to sine t plus c. Integral of cosine is sine, so sine t plus c. Now what we're going to dividing, we have y equal sine t plus c over t to the 5th power. We assume that t not equal to 0. Good. So if you know any initial condition, now we can use the initial condition to find it. Actually, you can use the initial condition even in a previous step. So like even you can use the initial condition here. Okay, so you can use the initial condition here. It's sometimes easy because once you find it, because you don't divide here, so sometimes you can do that also. Okay, so so we can use the initial condition now. So using the initial condition, we have 0 equal y to the pi over 2. So let's plug in pi over 2 whenever you see t. So it is sine pi over 2 plus c over pi over 2 to the 5th power. But see that this is equal to 0. So this says that 1 plus c. So right, the top is 1 plus c over pi over 2 to the 5th power, which is equal to 0. That means c has to be negative 1. Okay, c has to be negative 1. So, okay, so once you put the c equal negative 1, you get the solution. So thus we have y equal sine t minus 1 over t to the 5th power, where t not equal to 0. We assume that t not equal to 0. Good. Okay, so that's the whole problem. Good. So so let's look at some exercise problems. So this exercise number 3. The first question is t to the squared dy over dt minus 3t y equal to. So the second question is x dy over dx minus 4y equal x to the 6th power e to the x. Okay, so you can try these two problems as exercise, and you can see the answer in the description. Okay, so let's continue. Let's do another type. So you can see that all problems are different from each other. So let's do another type of problem. So the next one, so example number 4. So example number 4, solve x y prime plus x plus 2 y equal x to the cube e to the negative x. Okay, so you can see that there's a different term, and this is also not in standard form, so you have to divide. So the answer, dividing by x. Okay, you divide by x. Once you divide by x, this is going to be dy over dx plus, if you divide by x, this is going to be 1 plus 2 over x. Y, if you divide by x, this is going to be x squared e to the x, e to the negative x. Okay, actually let's put a 10 in front of this problem just to make it like a little interesting, little bit more interesting. So I'm gonna add a 10 in front of this. Okay, so here and there. So let's slightly change the problem to 10 x cube e to the negative x, and here also so you divide, so it's become 10 x squared e to the negative x. Perfect. So now what is the integrating factor here? What is the integrating factor? So you can see that the integrating factor now is this part, so that is the px. This whole thing is px. Okay, so you can see here px equal 1 plus 2 over x. So the integrating factor ix equal e to the integral of 1 plus 2 over x dx. This is not that bad. Integral of 1 is x, 2 over x is 2 ln x, being 2 inside, so it's going to be e x plus ln x squared. Now what we can do, we can split this as ex times e ln x squared, and as we discussed before, this part get cancelled out, so you end up getting x squared ex. Okay, so you're getting x squared ex. So now what we can do is just the same thing. After we do that, multiply by the integrating factor. So multiplying by ix, so we have d by dx. Here it is y times the integrating factor is x squared ex. On the other side it is 10 x²e to the negative x times x²e to the x, and you can see that these two terms get cancelled out. So you're gonna get 10x⁴ power. Now what we can do, we can integrate. So integrating, you can have y x²ex equal the integral of 10x⁴ power. So this is an easy integral, just use the power rule, x⁵ over 5 plus c, that means 2x⁵ power plus c. So this is going to give you the solution. So what's the solution? If you divide by that, so you're going to get y equal 2x⁵ power plus c over x² to the x. Okay, and here x not equal to 0. So that's the solution. So you can see that you can do this whole problem in just one page, or not even one page, it's like half a page. It's not difficult, but you need to remember how the steps. Okay, it's not a difficult problem, but you need to remember the steps. Good. And then if you are given initial conditions, you can use the initial condition to find c. So I'm going to give you two practice problems. So exercise, this is number 4. The first problem is x dy over dx minus x plus 3 y equal x⁵ power e to the 2x. Okay. Good. And then part B, x plus 1 y prime, that's a derivative, plus y equal natural log x along with y1 equal 10. Okay, so try those two and you can find the solutions in the description. Good. So let's try to do one more problem, and so this time what we're trying to do, I'm going to do a problem from a piecewise function. So this is the last problem we try. So example number 5. I'm going to put a star here because this is a slightly different problem, also it's like application. So piecewise linear differential equations. So piecewise linear differential equations. Actually this is a nice application. You're going to see this kind of application in electrical circuits. For example, when you charge a capacitor. So if you charge a capacitor, let's say this is a circuit, say a switch, and you're going to see a power source. So what we can do, we're going to switch on. So it's a capacitor, we're going to and then this is a power source. You're going to switch on and then wait a few seconds and switch off. So what is the charge? What happened to the charge of the capacitor if you start with a 0 charge? So and then you can see that that's going to create a differential equation, and the differential equation of this type actually. So we can solve that differential equation and see what's going to happen. Okay, so so solve. So you're going to get a differential equation like this: dy over dx, in this case dt if you want, plus y equal fx along with y0 equals 0 because the initial charge is 0, and then where fx is a piecewise function or a switching function, it is 1 in between 0 and 1, and then 0 after that. Okay, so what we do, we can switch on for 1 second and they switch off. So the question is, what is the charge? Okay, what the charge gonna behave? So the differential equation for this one gonna be like that. We can discuss later when we talk about applications. Good. So let's try to solve this equation. And so actually, what is the graph of this one? So the graph is like this. So you can see, so it is 1 from 0 to 1, and after that all of a sudden is 0. Okay, so this is how the switching function or the input function. So this is what we normally call input function. Okay, input function. And then you're gonna see what the output looks like. Okay, so input function. It's not an impulse differential equation. We can do impulse later, but this is a switching function. Okay, so what we can do, and you can see that the fx function changes. It's not different. It's not the same. So what we can do, we're gonna solve this problem as 2 steps. Okay, so we're gonna solve for one piece first, and then the next piece. So the answer, find, let's say first on the interval, that doesn't look like interval. First on the interval, 0, 1. So we can solve on the 0, 1 interval. So in that case, your differential equation becomes dy over dx plus y equal 1, right? Just 1 on that interval. So in this case, you can see px is equals to 1. The integrating factor ix is e to the integral of px dx, which is e to the integral of 1, so which is e to the x. Okay, e to the x. So that means your differential equation looks like this. It is d over dx y ex equal ex, integrating, we have y ex equal integral of ex dx, and then we have ex plus, I'm going to call it c1 here. So that means if you divide by ex both sides, you're going to get y equal 1 plus c1 e to the negative x. That's the first part. Now what we can do, we know the initial condition. So since y0 equal 0, we have 0 equal 1 plus c1 e to the 0. This is going to give you c1 equal negative 1. So that means your solution y equal 1 minus e to the negative x 0 x to the 1. Okay, so between 0 and 1, this is how it looks like. Now what we can do the same thing for x greater than 1. We have dx over we have dy over dx. We have dy over dx good, dy over dx plus y equal 0. It is 0 on that side, and then it's very similar. This side is not the same, so it is y ex, same integrating factor, is equal to 0. If you integrate, you're going to get y ex equal only a constant, and then this can give you y equals c2 e to the negative x. So that means you can write the solution like this. So you can say, okay, so solution equal, it's a piecewise function. So you have first 1 minus e to the minus x on the interval 0 to 1, and we have c2 e to the negative x on the interval actually for x greater than 1. So that's what happened. Now the thing is that if you need a continuous solution, so most of the time for these kind of situation, like a switch on off situation, the solution has to be continuous. So that means we can use the continuity at 1 to find C2. Okay, so let's use the continuity at 1 to find the constant. So assuming the continuity at x equal 1, we can say C2 e to the negative 1 equal 1 minus e to the negative 1, and then you can solve for C2. So this says that C2 equal e minus 1. Okay, if you multiply by e both sides, you're going to get e minus 1. Okay, so then the solution going to be y equal 1 minus e to the minus x for the interval from 0 to 1, and e minus 1 to the e to the minus x for x greater than 1. So that is the solution of the piecewise linear differential equation. So let's look at the graph of this function. So what's going to happen from 0 to 1? You can see that if you plug in 0, it's 0, so start with 0, and the part that you're going to subtract going to decay. That means it's going to increase, and then after that, if you plug in 1, you can see that they are the same. If you plug in 1, you're going to get they are the same, and then after that what will happen, e minus 1 is a constant, and then e negative 1 decay, so it's going to go down. So that means your graph going to look like this. So so it's going to start with 0, and this is 1. So what's going to happen, so it's going to increase, start with 0, it's going to increase, and I'm going to go like that, and then after 1 it's going to decay like that. Okay, so that's the so that's what happened. So this is the y. So this is a good example for a electric charge. So its x is actually time here. So you can see that. So this is the part e minus 1 e to the negative x part is a decay part, and this is 1 minus e to the minus x part. Okay, so this is a like kind of a nice example, as I told you, like if you have a capacitor, and then if you're gonna charge it, so how the electric charge gonna change. So you're gonna put some power source here, and how the electric charge gonna work. C. So let's say so y is the electric charge. Okay, so this electric charge. So this is a nice example and how to use differential equations to find solutions to real world situations like that. Okay, that's good. Okay, so I just want to write something like a description about another case, what we call singular solutions. So I'm going to write a note. Singular solutions. Singular solutions. Singular solutions. So consider ax dy over dx plus bx y equal cx. So let's say so if you see a point where the ax function becomes 0, you call those are singular solutions. So like ax function, first the coefficient of the derivative term. So let's write it points x naught such that ax naught equals 0 are called singular points, singular points, and leads to a discontinuity, in the solution. Okay, so there are cases like that. For example, in problem 4, of example 4, for example, has a singular point at x equals 0, and it appears that the solution y equal 2x⁵ plus c over x⁴ex is also discontinuous at x equal 0. So that's what happened, that singularity carries over to the solution. Okay, good. So those are what we call singular solutions. So this is a singular solution that doesn't exist at x equals 0. Okay, so there's a nice observation. So there are some problems, I just write this as an another note. So there are some problems that can be converted to integrating factor method. So for example, I'm going to give you just one example like that. So let's say dy over dx equal 1 over, let's say, x plus y squared. So if you see this problem, you can see this may not look like it is the right form, but if you turn it upside down, what will happen? You turn it upside down, it is dx over dy. You can see that it is x plus y squared. That means if you bring it to the other side, it is a integrating factor problem. Okay, so this can be a integrating factor problem, because you can rewrite this one as dx over dy minus x equal y squared. So you can see that this is a nice simple problem that you can try. Okay, so this is a integrating factor problem again, but not with respect to x, but with respect to y. If you take y as the dependent variable, you can try this problem as well. So there are like interesting things like that. It doesn't look like, but you can turn this into a integrating factor problem. Okay, so you can convert it. Okay, so this is the end of the integrating factor method. Thank you.